STP, SATP, the combined gas law, and Dalton's law. So STP is a set of conditions that are quite common, and so a lot of people would refer to these particular set of conditions. So for example, a question may say a gas was under STP conditions, or an experiment was carried out at STP conditions. So these conditions are worth memorizing so that we can refer to them without having to constantly mention what the temperature and the pressure are if they are at these particular conditions. So standard temperature and pressure, that is when the temperature is 0 degrees Celsius, which means 273 Kelvin. The pressure is 1 atmosphere, which is the same thing as saying 101.3 kPa, or 760 millimeters of mercury, or 760 torr, if you want to use those units as well. So if you memorize what the conditions are torr at STP, it also helps you with the conversions between torr, millimeters of mercury, kPa, and atmospheres. So think of this as being at sea level in the wintertime. So you're at 0 degrees Celsius and you're at sea level. That would be the same. That would be conditions of STP. Most people don't carry out experiments at sea level in the winter. So we also have this other standard reference point of conditions called SATP, ambient. So standard ambient temperature and pressure. And this is more likely the conditions that an experiment would be carried out if it was carried out at the lab. So you can imagine instead of being at 0 degrees Celsius, an average temperature for a lab might be 25 degrees Celsius. And instead of being at sea level with an entire atmosphere above you, you're probably somewhere above sea level. So the pressure will be a little bit less than 1 atmosphere or 101.3 kPa. So SATP is 25 degrees Celsius or 298 Kelvin, and a little bit above sea level, so a little bit less atmosphere above you, and so the pressure would be a little bit less as well on average. And so we refer to SATP as 100 kPa and 298 Kelvin. Both two sets of conditions that are often referred to, worth memorizing. So we know a bunch of laws already. We know Boyle's law, we know Charles' law, we know Gay-Lussac's law. So Boyle's law talks about the inverse relationship between pressure and volume. As one goes up, the other one goes down, assuming temperature remains constant. Charles' law talks about the proportional relationship between volume and temperature. So if the temperature goes up, the volume goes up, and vice versa as well. So a indirect relationship is going to look like this, and a proportional relationship is going to be looking more like this. Gay-Lussac's law is similar to Charles in that it talks about a proportional relationship, but it's referring to pressure and temperature. So as pressure increases, so does temperature. So if you had an initial gas and a final gas under those two conditions, this is what it's going to look like. So what we can do is we can combine all three of these equations into one because they have similar terms. And we can do that mathematically. We could set the equations equal to terms and sub them in. That would work. But also, we just look at the relationships between the variables. We can kind of deduce the equation as well. We know that pressure and volume are inversely proportional. We know that volume and temperature are proportional, and pressure and temperature are proportional. So both volume and pressure are proportional to temperature. And if we look at how we have that relationship between them, so volume and pressure are proportional to temperature, whereas pressure and volume are inversely proportional. So the equation that involves all three of these terms is going to end up looking like this, where pressure and volume, just as Boyle's law states, are inversely proportional, but pressure and temperature are proportional, and volume and temperature are proportional as well. So this is called the combined gas law, and we have all three variables of pressure and temperature in one equation with the initial circumstances and the final circumstances for any given volume of gas. This is assuming we're talking about the same volume of gas. If you were to add more gas or take away more gas, this would not hold true. And if you look at this, if you take any one of these variables and you keep it constant, let's say temperature remained constant. So T1 right here and T2 here, if they were the same variable, we know mathematically they'd cancel out. So it'd be the same thing as saying temperature doesn't change. And as we can see, that's Boyle's law. That's what Boyle's law says. Pressure and volume are inversely proportional, assuming temperature remains constant. So if you have your combined gas law, if temperature remains constant, you have Boyle's law. And same thing for the other variable. If we looked at Charles' law, volume and temperature are proportional to each other, assuming pressure is kept the same. So imagine pressure was kept the same, and we kept temperature down here at the bottom. So T2, let me just rewrite T1 again. So if pressure's out of the equation because it's remained constant, it's mathematically eliminated itself, and we'd have volume 1 over temperature 1 equals volume 2 over temperature 2. Charles' law. And we can do the same thing with keeping volume the same for Gay-Lussac's law. So the combined gas law combines all three variables in one. Let's try this question out. So a sample of gas has a volume of 500 liters, pressure of 101.3 kPa, and a temperature of 273 Kelvin. You could say it's at STP conditions. Instead of stating the numbers, you just say at STP, and then the person working on the question would know that this is the pressure and the temperature. What volume will it occupy at 0 degrees Celsius and 93.3 kPa? So again, with any question where you have a lot of variables, half the battle is keeping track of the variables, and then looking at how they're related to each other. So there's our combined gas law. And if we write out the variables so we can keep track of them, making sure that we change Celsius into Kelvin, because we can't do any math with our temperature in Celsius. We have the volume under the final conditions that we're looking for. So we're solving for V2. So there's the question again, just written out on this page. So there's our initial combined gas law, and we want to isolate for V2. So we've got to get T2 out of there. We can do that by multiplying the equation on both sides by T2. You can do whatever you want to an equation as long as you do it equally both sides. That would cancel it out of the right hand side, and it would now be on the left hand side. Now to get rid of V2, we would have to divide both sides by V2. That'll cancel it out on the right hand side, and it'll show up over there on the left hand side. So wait a second, I'm looking for V2. I don't want to do that. I want to divide by P2 because I want V2 to be alone. So if I divide this side by P2 and this side by P2, it'll be eliminated from the right hand side of the equation. It'll be over on the left hand side, and I will now have my final volume isolated, which is what I'm looking for. Let me write that a little nicer, saying that V2 is equal to P1 times V1 times T2 divided by V2 times T1. Plug in your variables, and again, it doesn't really matter what unit we're in other than temperature, which has to be in Kelvin, but in terms of volume and pressure, it doesn't really matter what unit you're in. It just means it'll end up with a particular unit. So for example, if I leave my volume here in liters, I know that my final answer will end up in units of liters. kPa cancels out, Kelvin cancels out, and that's where I'm going to get my volume in liters. So final answer, 543 liters. Notice since the temperature didn't change, we still use the combined gas law, but because temperature was equal at the beginning and the end, we could have just eliminated it from there. Alright, Dalton's law. Fairly straightforward one. So we know him from the model of the atom theory, but he also did some work on gases, and essentially what he figured out was that if you take different gases that don't react, they're just hanging out together, if you take different gases and you put them all into the same container. So I take this helium, which has a pressure of 1 atmosphere, and I take this nitrogen, which has a pressure of 1 atmosphere, and I take this oxygen, which has a pressure of 1 atmosphere, and I put them all into this one container. The final pressure of the gases in that container is just going to be the sum of the pressures of the gases that were there beforehand. We can express this mathematically as the total pressure is equal to the partial pressures of each of the gases that are in the mixture. So if you have 3 gases added in the mixture, you just take their pressures, add them up, and you'll have the total pressure of what they would be in a single container, assuming you kept the volume consistent. You can do this for any number of gases. So we refer to the total pressure, and then each individual gas makes up a part of that total pressure, so we call it the partial pressure of each gas. So Let's try a question out with this. If 2.5 atmospheres of helium is added to a 1 liter container of oxygen at a constant temperature that already has a pressure of 1.2 atmospheres. So you've got a container, 1 liter container of oxygen, and its pressure is 1.2, and you add in this amount of helium, which has a pressure of 2.5, what's the final pressure? So we know the total pressure is just going to be the sum of the combined pressures. The combined pressure is 1.2 plus 2.5, so we'll end up with a total pressure of 3.7. The partial pressures add up to give you the total pressure. Let's add in some percentage calculation with this. So in the atmosphere, oxygen makes up about 23% of the atmosphere. So what is the partial pressure at STP? So we need to know how much pressure does oxygen exert in the atmosphere under STP conditions. If the conditions change, then it'll exert different pressure. But right now we know this is standard temperature and pressure, 0 degrees Celsius, 101.3 kPa. And that pressure of 101.3 kPa, that's a combination of all the gases in the atmosphere. So when you feel atmospheric pressure, it's all of them. 23% of them is because of oxygen. So what amount of pressure is that? Essentially, what is 23% of atmospheric pressure is what the question is asking for. So we know that at STP, the pressure is 101.3 kPa. We can do a simple percentage calculation. Essentially, what is 23% of 101.3? We can set it up in an equation if we want, but all we need to know is what is 23% of 101.3 kPa. Essentially, we're taking 101.3 and multiplying it by 0.23, and we would end up with 23.3 kPa as the partial pressure, or the pressure of oxygen within atmospheric gas.